Hello again. We are going to talk about chapter 12 in this chapter. In this video. I hope you're doing well. So let's get started. Turn off my video, we don't need it, and get into chapter 12. Now I'm going to try to do this in one video, but it might take actually two videos, but let's see. So in this chapter, we're going to talk about linear regression and correlation. Now we have seen this before, so I think I have shown you this graph. There are two variables involved. We did this in chapter 2 when we graphed the scatter plots. So we have two variables. The one variable here in this case is number of cigarettes smoked, and then this one is the relative risk of getting lung cancer. So as you see, these points, each point has to do with this person who has smoked this many cigarettes a day, right? The number of daily cigarettes smoked, and then the relative risk of getting cancer is right here. So usually these are given out of 10,000, but just a number. So now every point, so it's like that. Now if you look at the pattern, you see that there is a linear pattern going up from left to right. And this kind of relationship is called correlation. So these two variables are correlated, and since the slope of this pattern is a positive kind of going up from left to right, we call this positive correlation. So let me show you another example here. Here's another example. Beers drank, grade. So notice that in this case there is a negative correlation. That means the more of this, expect less of this, right? So that's called a negative correlation. Here is another one, quiz score and exam score. The higher the quiz score, the higher the exam score, right? You see there is a positive correlation. And here's another one, per capita daily meat consumption, and then here is colon cancer incidence per 100,000 women. So as you see, we are right here. That means American women consume this much grams meat per day, and our cancer rate is about that much. Now these people over here, they consume this much, so their rate is way over here. So you see, for example, difference between this level and that's 3 times more, right? All right, so that's positive correlation. Here's another one. Here is the height of the mother, and this is the height of the children. So the child of a mother, for example, that is this height, ended up being that height. The child of a mother that is, let's say, this height, ended up being that height, and so forth. So as you see, there is a positive correlation, right? And that means the higher this, the higher that, right? In general. And here is another one. This is father's height, and this is again the height of the children. So now, so what we want to do in this chapter is this. What we want to do is we want to, we have a pen already, okay. So what we want to do, let me go back to this one. So what I'd like to do is, what we want to do is this. First of all, we want to be able to graph these points and look at the pattern. That's the first thing we want to do. But then we're going to talk about a number that tells us how strongly these two variables are correlated, and we're going to call that number R. So R is a number that tells us how strong this correlation is. We're going to calculate that. Calculator is going to calculate it for us. I give you the formula, but that's what the calculator does for us. We also want to know if there is a pattern, if there is a function, which is, in this case, in our chapter, is going to be a straight line. Is there a straight line that goes through these points and is closest to all of them? And this straight line will have an equation, and we're going to find that equation using calculator, right? So that's the idea. So, and we're going to call that y hat, which is the predicted y value for these points. So if we want to connect this to chapter 9, this is the idea. You see, here is the population of all, let's say, mothers and their children. Now, we don't know the correlation between all of those points. There are millions of points, maybe. There are like a whole lot of points. Maybe there is a positive correlation between them, right? So maybe there is a positive correlation. We don't know. And of course, there is a value. And that number that we find here, we call it R. For the population, we call it a rho. This is a rho. It looks like a P, but it's rho. So, and also the population has a line that goes through these. We don't know that line either, right? So that line is y equals to alpha plus beta x. And we're going to talk about this, right? I'm just giving you a general picture of what we're going to do in this chapter. Okay, so that would be the equation of that line that we don't know. And this is rho, is the strength of the correlation that we don't know. Then we take a sample, and this is the sample, right, of some mothers and their children. And then we're going to calculate what? We're going to graph the points, like we did right there. We're going to find the correlation coefficient, which is R in this case. I'm going to find that. And also we want to find the equation of that line, which is going to be y hat. And that's going to be, we're going to call it a plus bx. Okay? So there were several parameters here. Remember parameters and statistics? So the parameters are y, alpha, beta, and rho. We have no idea what these parameters are in the population. What we take a sample, and from the sample we find y hat, a, b, and r. Okay? And you might ask, why do we want to find the line that goes through these points? It's because we want to use it to predict. If we find a mother, for example, that is this height, we are going to go to the line right here. And of course, I have to go straight. This is not straight. So let me erase that. All right, so let's go straight here. We go to the line, and when we go to what? We go to the y-axis, and that gives us a predicted value for that x value, right? So if this is x sub I, let's call it x sub I, we don't know which one, this would be y hat sub I, right, for that x value. And that's why we are interested in finding y hat. And of course, y hat has to do with a and b, and also has to do with r. So at the end of this chapter, we're going to do hypothesis testing for this situation, because we found an R and we find this B and all of these numbers that represent what? That estimate the parameters, but we don't know, right? Just like chapter 9 or chapter 8, we don't know these values. So if somebody says that rho is 0, that means there is no correlation, and then we find R to be some number that is not 0, then we can what? We can do a hypothesis test. But all of that we're going to talk about. This was the general picture of what we do in this chapter. So let's move on. So the first thing we want to do, of course, is in general, this thing happens with one response variable and then one dependent variable and one independent variable in this chapter. So in this chapter we have one y, and then we have what? We have, so let's make it y hat so we can use a and b. So we have just one x. But in general, in application problems, we have something called multiple regression. So this is called regression, linear regression. This one is multiple linear regression. It could also be nonlinear, but we're not going to talk about it in this chapter. So you can have something like that. You might have a sub 0 plus a1x1 plus a2x2, and you can have more than one. So let's say ak, xk. So you can have a situation when one thing depends on what? Many other variables. We're going to kind of mention this at the end of the chapter, but we're not going to talk in details about it in this course. So here's an example. For example, the income. Someone's income might be related, dependent on number of what? Number of years of education, kind of profession that they're in, number of years of experience, and the ability. So you see, there are many factors involved. We are going to talk about only do calculations for a situation where when we have one dependent variable and one independent variable. Okay, so let's get started. So we talked about that already. So let's do some examples. We did this in chapter 2. We graphed the scatter plot. Let's just do one actually. So before we do that, from algebra, you know about linear equations. Remember y equals to mx plus b, where this was the slope and this was y-intercept, right? We had something like that. So this is the y-intercept, and the slope is the slope of this line. Now, here in statistics, we're going to switch these two and change the letters. So instead of writing mx first, we're going to write it second. And then we're going to change them to a and b, right? Of course, in this course, we're going to always call it y hat with a and b. But this is just algebra, okay? So there is an example here. It says that there is a company that charges for word processing. The rate is $32 per hour plus 31.50 flat charge. So the total cost, of course, depends on what? If I call this total cost, that would be what? That would be 31.50 plus $32 for every hour, right? So that's an example of a linear equation. And I'm going to show you right here. So here is the idea. So x is the number of hours it takes to get the job done. Y is the total cost. And you can write it this way. This is from algebra, something simple. Now, in terms of equations of lines, we can have all kinds of lines. We can have horizontal lines. That means the slope is 0. We can have lines that from left to right, they go up. That means the slope is positive. And lines like this one, from left to right, they go down. So the slope of that blue one is negative. See that? So these are some examples of the straight lines from algebra. Okay? Now, I go with certain pace here, but you can stop the video, go back, rewind, and listen again, and think about these things, take notes. All right, so scatter plot. So we know how to graph a scatter plot. So let's do this. I'm gonna show you in the calculator because I want to do another one which has more numbers with the calculator and show you. But here we have data for this situation where Amelia notices that the number of points she scores in a game goes up in response to the number of hours she practices. All right, so these are number of hours she practices, and these are number of points that she makes after practicing that many hours, right? Now the question is, let's look at the question. So it says construct a scatter plot. We did that in chapter 2, so I'm going to just show you with the calculator how this is done, and then we do one. I actually enter it in the calculator. But here you go to Stat, Edit, right? You can stop the video and put these numbers in L1 and L2 if you want to follow me. So L1 and L2, we put these numbers, and then we go to Stat Plot, second stat plot. We pick the first one and we turn it on. And we pick that one, scatter plot, and then L1 and L2, and we pick one of these marks. There are 3 marks because there are 3 plots. So we pick one of those, and then we go to zoom 9, and you should see these points graphed. Now, the question is, should she believe that there is a positive correlation between number of hours she practices and how many points she makes? Yes, there is evidence here for positive correlation, as you see, linear positive correlation, right? That's the idea. All right. Now, the question is the strength of the relationship. We can look at the scatter plot, for example, here. These two, both of them have what? Positive correlation. But if you draw a line through the points, right, like this, and you see that in this case, there are some points, like this one, that is far away from the line, and here most of the points are close to the line. So the closer the points are to a straight line, the stronger the positive correlation or the negative correlation, right? So the closer they are to a line, the stronger the correlation. Of course, horizontally, if the points look like that, this is no positive correlation because the slope is 0. So it has to be slanted like those to have correlation. All right, so which one of these is stronger? This one. So for example, here we have a negative linear pattern that is strong because you see they're all close to a straight line. Here we have negative, but is weak. Why? Because if you draw a line here through them, you see they're far away from the line, right? But here they're like all close to a line. Here, this is not even linear because it's exponential, you see. That's not a linear growth. And if it looks like that, you can't make any slope out of this. It looks like it's all over. That is no pattern, so no correlation. All right. For example, here we see which one of these is a stronger correlation. Well, this one, because you see they're much closer to the line, and these are a little bit, there's a distance, right? This one. All right, now that the question is, how do we calculate a number that tells us about the strength of the correlation? And we're going to do that with a calculator. So So data, usually these points never exactly fall on a straight line. They're all over, right? But we are trying to find a line that goes through these points and is closest to all of them. That becomes tricky to find actually, because you have to minimize the distances of all the points to this line. And that requires calculus, linear algebra, and differential equations. Do we have those three in this course? No. This is algebra based, so we are not going to do any of that. We are going to use calculator instead of calculus and find the equation of the line. Okay? So how do we do that? Well, again, to use a calculator, you put the numbers in L1 and L2 again. You can stop and put these numbers in the L1 and L2. Then second stat plot, you go to second stat plot and you pick the first one, a scatter plot, and pick that mark, L1 and L2. Then you go to zoom 9 and graph it, right? Now here is something that the calculator comes with this feature off, and we need to turn it on. So that feature is something called, let me get out of here. So if you go to second catalog right here, and then go to letter D right there, then scroll down to diagnostic on. You see, off and on. I'm gonna turn it off because mine is on. I'm gonna turn it off, so it's off now. Now if I so I have a different set of values in my stat because the next problem has those numbers. So I have these numbers. It's not the same as this. It's not the same as these numbers here. So I'm going to use these numbers and go through this. So what I do, if I go to stat plot and turn it on, right? Now when you do that, make sure there is nothing in y equals to, because otherwise it would graph that at the same time. We don't want that. So then I'll go to zoom 9. Well, go to stat plot. I picked the wrong one. So I want this one. I was doing something else. I was doing box plot, right? So I go to zoom 9, and you see the points. My points are different from yours, of course, here in this problem, but it's the same thing. Now, if I go to stat, calculate, and then go to number 8, you see number 4 says linear regression, ax plus b. Number 8 says a plus bx. So in algebra we use that. In statistics we would rather use this one. So it's okay if you use that one, but you have to make sure you know a here is the slope and b is the y-intercept. Here a is the y-intercept, b is the slope. Okay, so let's pick that one. And what this does, the calculator is going to find that line for us that goes through the point. But also it calculates that R for us. You see, two main things we wanted to do, calculator does it for us. So right after it, you're going to put L1, comma, L2, right? And if you press enter, you see, now it calculates the line for us. You see, this line is negative 173.5 for A, and then B is this number. But notice it doesn't have R. But I'm going to show you in this case here. Oops. I wanted to go here. And so that's turning on that. Get this out of the way. And when you do this, you see what it looks like? It's got R and it's got R squared, but mine doesn't have it. You see it? Let me do this one more time. You see? It's not there. Now I'm going to go turn on what? Turn on what we just talked about. Diagnostic what? On, which is right there. I'll put it on home screen and press enter. Then I'm going to go back to stat, calculate, again number 8, and the same thing, L1 comma L2. That's not L1. Second on, and then L1 and comma L2. Now you see how I have R and R squared. Of course, my R and R squared are different because there are 4 different set of numbers. Okay, so that's how we find that equation for the line. Okay, so remember in the graph now we have a bunch of points, and then we have that equation, but that equation is not here. You have to graph it here. Now to graph it here, we go to y equals 2, and then we're going to find where the calculator stores that equation. And it stores it under variables. And where do you think it is? Well, statistics, number 5. And where over here is it? Well, we're looking for an equation. Well, look, EQ right there. And it's the first one, regression equation. And if you fetch that, it goes directly right there. See? And now when you graph, you got the points and you got the line going through them. Now we're going to need this in a second. So we did it already. So it's in my calculator. So I'm going to move on. So that's the idea of regression equation. I'm going to show you the formulas, but we're not going to use the formulas in this course directly. All right, so that's it. So this is the process of graphing bunch of points, finding the equations for them, and also find what that number R that we're going to talk about in a second. All right, so here are the numbers that I actually wanted to work with, because we're going to work with these numbers for this video. So you might want to stop the video here and put these numbers in L1 and put these numbers in L2. Make sure you don't make a mistake. Check, double check. Then we're going to continue. So I have them already in my calculator. So I have them already here. I did it before I started the video, so I don't have to spend time doing it. You see, I have the numbers here already. Okay, so go ahead and put these numbers in L1 and L2 and pause the video and come back. Okay, so now that you're back, it says a random sample of 11 stat students, right? 11 statistics students produced the following data, where X is the third exam score of 80. So third exam score out of 80. So the highest points you could make is 80. And then Y is the final exam score out of 200. Can you predict the final exam score of a random student if you know the third exam score, right? So the question is there a correlation between what? Between the final exam score and third exam. That means if I know that a bunch of students average, for example, 71 on the third exam, can I say those students average on the final what that would be? Yes, I can make a model here, create a model and use it to predict, right? How do we do that? Well, first we graph the points, and we know how to do that. So we put the points in the X values and Y values in L1 and L2. So these are third exam scores, and this is final exam scores. Then we go to stat plot. We pick the first one, we turn it on, pick the scatter plot, make sure this is L1, L2, and then pick that mark. And then let me do this one more time. I'm gonna take it away from there, and then run that, right? So I got that. So I got, just a moment, let me go to Zoom 9. Okay, I got the graph. Then I go to Stat, Calculate, and I'm going to run that number 8, which is linear regression. And then I put L1, comma, L2, and here we go. So what I have is an equation that goes through these points and is closest to all of them. Now, that is actually a pretty a difficult problem to solve, but as I said, we can use calculus, linear algebra, and differential equations to find this line, but the calculator is programmed to do it. See, it did it already. So we don't have to worry about that. And also, we can find a number that tells us how strong the relationship is between these two variables, and that number is 0.66. And in a moment, we're going to talk about what that actually means and what is the range of numbers R can equal to. But for now, R is the strength of the correlation. It's called correlation coefficient. And then this is the equation of the line. So if I put this again in y equals to, right here, I go to variables and stat, equation, and it's the first one. There, and then graph, it goes through them, right? So far we know there is a linear correlation between, there is a linear relationship between the third exam scores and the final exam scores, right? All right, so it says in this example, the third exam scores that we talked about, we can predict that the final exam scores of a student whose score on the third exam is 76 out of 80 will be about 194 out of 200. How do we do that? Well, it's easy. All we have to do is figure out if somebody made a 76, so 76 is somewhere over here, out of 80, then what would the score be out of 200? Well, what we're going to do, we go to the line here, and we go left to y-axis and find this number. There are many ways we can do that. One way is to go to home screen, clean it up, and then go get what? Go get this y1, and then find y1 of 76. So let's go find it. Where is y1? Let me get. Now y1 is also under variables, and is under y variables, and under function, right there, y1. You press enter, bring it to home screen, put parentheses, and put 76. There. So according to our model, the final exam score, average final exam score for those students who average 76 on the third exam is about 193 out of 200. That's our prediction. Okay? Now we could have just used like only a few decimal places, maybe 2 decimal places, and use it and do it by what? By hand. But the calculator uses all these decimal places, so it's the more accurate answer calculator can give us. Okay, so that's the idea of this chapter. We have a bunch of points, a sample, and then we find R, and we find a line, and we use it to predict. All right. Well, of course, the line doesn't go through the points, so there is a difference, right? So for example, this is the x value here, this x value, let's call it x1, right? This is x1. That value right there, this distance here, is actually y1, right? And this distance here, from here on the line to this, that's y1 hat. That means this is the value that we predict for this x value. Of course, the observed value is that one, right? So y sub I is observed value, and y hat sub I is predicted value. When we subtract observed minus predicted, we get this distance here, right? And that distance is the error number 1. So it's the error for what? For x1. There is an error. That means our line made a mistake, right? Or that is some kind of error. But there is an error according to our model, because model says that for x1, y is supposed to be here, but then the observation says y is over here. So there is a difference. And that difference is given by this y sub I minus y sub I hat. And then you take the difference and you square it. Remember we did variance? We said that if we add all the differences, we get 0. It's true here too. So if we find all these differences and then add them, we get 0. So what we're going to do, we're going to square them so we don't get 0, and then add them. And we call this the sum of squared errors, right? This is the sum of squared errors, right? That's the idea. All right, so that if you take the square root of this and divide it, if you divide it by some number of items minus some number, remember that? I'm going to talk about that. We can find actually square root of it, and the square root of it is the standard deviation of the errors. So what the line does here, and we're going to talk about this again in a second, but for now, what the line does for us, it minimizes all of these distances. And that is tricky to do mathematically, but since the calculator does it for us, we don't have to do it. But we have to understand what the line does. The line minimizes these distances, so we have the best model possible here. And that is this right here that we got with the calculator. All right, so the formulas that we don't use are these formulas. So in order to find this line, you have to find this b first, right, which is this formula. Is basically getting every x, subtract the mean, every y, subtract the mean, and multiply them and add them all. And then, right, this doesn't make any sense, to us, because we didn't go through the process of actually finding it. But we understand that this is the slope of the line that we want, and the calculator does it for us. Now, when you find these lines, because of the way we calculate these lines, there is a point that is always on all these lines, and that point is the point that the coordinates of it are x bar and y bar. Now you know x bar is the x average of all the x's, and then y bar is the average of all the y's. The way that we calculate regression line kind of guarantees that this line goes through that point. So once we find b and we find x bar and y bar, then we can find a, right? That's the process. But we are not going to do it this way. We already know how to find the equation of the line. And this line is called regression line, or you can call it the line of best fit. That means it's the line that best fits the data that we have here. All right, so the slope of the line is related to that number r that the calculator finds. And the relationship is basically the standard deviation of the y values divided by standard deviation of the x values times r gives you b. Or you can multiply by reciprocal of this. If you have b, you can find r. But of course, with our formula, we find b first, and then we know b is this right here, so we can get r out of here if you multiply it by reciprocal of this. Okay, so that's the connection between b and r. They're related. That means if the slope is positive, then r is positive as well, and the other way around. So r and b have the same sign. They cannot have different sign because this right here is positive. Remember, these are standard deviations. All right. So interpretation of the slope. Well, you know how to interpret the slope, so I'm going to go to the example here that we found. Remember, this was the equation for the third exam versus final exam. We found the line that goes through all the points. So this right here is the slope, which we put a 1 under it. So it says for every 1 point that the average on the third exam goes up, the average on the final goes up 4 units. 1, 2, 3, 4. Makes sense? So for every 1 unit, the average on the third exam goes up. The final average goes up 4.83 units. That's the interpretation of it. For a 1 point increase in the score on the third exam, the final exam score increases by 4.83 on average, right? All right, so how do we find R? Well, here we go. Well, all of these are in the calculator, and you can actually use this formula with the calculator. If you go to variables after you do the regression, if you go to variables and go to statistics, you see they're all right on their sigma. See, all of these like sigma xy, sigma y, sigma x squared, they're all right here. You can put them in this formula right here and find r. But why? That's a waste of time because calculator finds r for us already. Well, that's the formula. And there is an easier formula, which is this right here. So you could also find r this way, which is basically finding all the z-scores for x values. See, I found them here with Excel. You don't have to really do this because calculator finds r. But that's another formula in case you want to practice with it. So these are the z-scores for x, and these are the z-scores for y. If you multiply them, you get these, and if you add all of these, you get what? You get the sum of them, and then divide by total number of data points that we have, we get r. And that's the r that we found with the calculator, right? This is not the example of third exam, and is another. You can actually practice with this, put these in L1 and L2, find R, and see if the same as this one. And you see that they're the same. But that's another formula to find R. This has to this example of advertising expenses and company sales. All right. So what does the value of R tell us? Well, let me show you. So if we have a bunch of points that are exactly on a straight line like this, then R would be 1. If we have a bunch of points that are exactly on a straight line this way with a negative slope, then R would be exactly -1. If we have a bunch of points that are on a straight line with a positive, but they're not exactly on a straight line like that, but they're very close to it, R would be close to 1, but not 1. So it would be R would be less than 1, but would be greater than 0, right? Now, if you have a bunch of points, not in a straight line, but exactly on a line, but negative slope like that, then R would be, of course, is not going to be -1. It's going to be greater than -1, right? But it's going to be less than 0, something like that. Closer to -1 than to 0. And of course, if you have horizontally like that, R equals to 0. And that's what R is. So R basically is from -1. It can be from -1 to 1, depending on the strength of the correlation. The closer it is to 1, the stronger it is, positive correlation it is. The closer it is to -1, the stronger negative correlation we have. Okay, so that's the idea of R, and I have some examples here. You can just, think of examples. I just use a function. For example, on the first one, I use 2x plus 1. So basically, every x value is going to go exactly to the same point on that line, right? So this is an example of R equals to 1. Then to get an example of R equals to -1, I just use a negative slope here. I made the slope negative and found these points. If you graph these and find R, you see that it's going to be -1. You can practice and see which are calculated. And to come up with a slope of like close to 0.9, I just took these and changed them a little bit. I tweaked them. So instead of 3, I put 2.9 and so forth. I went to the, up and down a little bit. And now I have R that is not 1 for sure, but is something close to 1. And to get the -0.9, I did the same for this one. Just tweak these numbers a little bit. All right, so that's R. So positive value means that the more of this, expect more of this. Negative value means the more of this, expect less of this. And 0 means no correlation, right? All right, so going back to our example, what was R for our example? Well, R, for example, was 0.66, right? So X is the third exam out of 80, and Y is the final exam score out of 200. So find R and interpret it. So R is 0.66, so there is a positive linear relationship, right? There's a positive linear relationship here. It's not as strong as 0.9 or close to 9, but it is greater than 50%. So there's a pretty good correlation. All right. Now, the correlation of determination is something else that we're going to talk about. The correlation of determination says this. For example, if somebody makes this much on the final exam, now I want to know the reason that student actually made that score. I say, okay, I have a model. So part of this has to do with what? The reason the student had made that high up to here, I expected already. That has to do with what? The model. But the rest of this, I'm not sure. So if we take this R and square it, we get the correlation, the determination. So it's is the coefficient of determination. So if I take this R and R squared, this number is the coefficient of determination. What does that mean? Well, we have to convert it to percent. So move it to the right 2 places, right? See it? So I get about 44% if I round it, right? So that means when I see somebody make some grade on the final exam, I say the reason that person made that grade on the final exam, 44% of it has to do with what? Has to do with the fact that they made this grade on the third exam. So the fact they made this grade on the third exam, 44% of the reason they made that grade on the final exam is because they made this grade on the third exam. But not all of it, only 44% of it. So 56% of the reason that this student made that grade, I have no idea. It could be, again, the rest of it, maybe 100% is this, but I don't know. I don't have evidence for that. I only have evidence to conclude that 44% of the reason that the person made that score has to do with the third exam score. 56%, I don't know, right? All right, so let me continue here. And this is the same thing I just talked about. So let's look at this. So R squared is about 0.43 or 0.44. Approximately 44% of the variation, right, in the final exam grade. The reason that the students make these scores that go up and down, this is variation, right? The reason that these scores vary, 44% of it has to do with the fact that the third exam scores vary, right? They go, up and down. That causes this going up and down in the final exam scores. How much of it? 44% of it. 56% of it, there are other factors involved, or could be this, but we don't have the evidence for it. Could be maybe they got sick on that day, maybe other reasons. 56%. All right, so we talked about that already. You can stop the video and read this. We talked about this. It says find R squared and interpret it. That's what that is. And again, how do you find R squared? R squared, well, you find R, and R squared is right there. All right, so here's an application of it. The American Statistical Association wrote a letter to school districts that kind of they thought that the variation in test score for students had to do with how good the teacher is, 100% of it or most of it. So they did a study on data, and they figured if you take all the mega data they have for all students in the United States, if this represents how good the teacher is, they put some numerical value of it based on number of years of education, experience and all that. So they gave every teacher a number. So this is how successful the teacher is, how good the teacher is. And this is how well the students did on the tests, standardized tests. And they found out that the connection here, there is a line, of course, there is a positive correlation. So there is an R. But they found R squared, and R squared was between 1% and 14%. That means in the best scenario, the best teacher, can only affect 14% of the success on standardized tests, from 1% to 14%. So that means in the best scenario, best case scenario, 86% of the success that students have on the standardized test has nothing to do with the teacher based on the evidence. In the worst case scenario, 99% of the success of the students has nothing to do with the teacher, how good the teacher is. There are other factors. So they wrote a letter to mention that ranking teachers by their VAM, that's the value added measure that they use, the VAM scores, can have unintended consequences that reduce quality in K-12. All right, so that was an application for the coefficient of determination, and I talked about that already. All right, so now I'm going to stop this video right here and make another video for the rest of chapter 12. For the rest of chapter 12, this is what we want to do. Once we have, remember, we have a population, and in the population, we have a whole lot of points that we have no idea about. And then we have a line that we have no idea about. And we have a correlation coefficient, rho, that we have no idea about. So there is y equals to alpha plus beta x that we don't know. And there is rho that we don't know, right? And there is rho squared that we don't know. All of that we don't know. So what do? We take a sample. And from the sample, what do? We found a line which is y hat, and we call it a plus bx, and then we have r. Now the question is this r the same as that rho? Is this line actually this line? And remember, in chapter 9, what do? We have to what? We have to do hypothesis testing. And that's what we're going to do the rest of this chapter. So I'm going to stop the video at this point and go here and say bye and take care of yourself and others, and see you in the next video.